Whenever you get questions like this where they give you the number of marks awarded, in this case 3 marks, just try and say 3 things, because normally if you are asked, well, what is the photoelectric effect, you might be tempted to say, well, it's simply the phenomenon where electromagnetic radiation hits a metal and electrons are ejected. And that might give you 2 marks, one for saying that electromagnetic radiation is involved and electrons are ejected or emitted. That would be enough. But that would only be 2 points, and we need at least 3. So it's probably worth, as a matter of course, saying as much as you can about it. One of the things that they did ask, or did require you to say, was that the frequency of the radiation that you use has to be greater than the threshold frequency. And the reason for that is that the energy of the incident photons has to be bigger than the work function. And what they're referring to there is that if this is the diagram of the metal lattice, the metal structure, these circles are meant to be ions. I added little plus signs because the metal ions are going to be positive, and these are the electrons you're going to try and eject. Now, when you draw a little box around it, they sometimes refer to that line as being the surface of the metal. I like to think of it as being the escape position, and if the electron manages to get to that position there, basically it's got out. Now, when that electron has to escape, it's got to get to there. I'm going to call that electron A, and I'll refer to it a little bit later on. But you're going to get that electron out by shining in light, which delivers its energy in lumps, discrete energy values. And I'm going to draw that as a little wave packet, which is what they do sometimes. And Einstein said that the energy of a wave packet is given by the formula HF. Now, if you want that electron to escape, it's got to get from there to there. The ions will try and pull it back, so you've got to give it potential energy. In fact, it's electrical potential energy. There will be a minimum amount required. This electron is the easiest one to get out. That one is more deeply embedded. This electron B, it would need more energy to get out. So we're talking about the easiest electrons. For example, that one there. And the minimum energy required to get it out is going to be supplied by a photon. And because it depends on the frequency, then the frequency will be the lowest frequency that will get an electron out. Very energetic photons won't just get the electron out, it'll get the electron out and it will give it some kinetic energy as surplus. We're just talking about an electron just getting out, no kinetic energy available to it at all. So that's the threshold frequency. And you've got to shine in radiation, which is an energy at least as big as the work function. So that the threshold frequency I've talked about in this particular answer. The energy, of course, needed to get from there to the escape position, that is the work function. And they're going to ask you to work it out. It does tell you the threshold frequency for zinc. 1.04 times 10 to the 15 hertz. Well, if you know that, and you know the formula for the energy of a photon, which is HF naught, that minimum amount is the work function. There's Planck's constant, there's the frequency you've been given, and that's the energy. Now, typically these energies are something times 10 to the minus 19 joules. So this is where they introduced the new unit of energy called the electron volt. We needn't worry too much about how they decided what an electron volt was, but it's that value there, that number of joules. So all you do is ask yourself, well, how many of them, which is 1 electron volt, how many of them are in that? And you do a division process, and it's usually 2, 3, 4 or something like this. 4.31 in this case, 4.31 electron volts. Now part 2 then says that you are dealing with a piece of zinc illuminated by radiation of a single frequency. So you could argue it's going to be monochromatic light. Maybe it's a laser or something like that. And it says that when you look at the emitted electrons, they've got a range of kinetic energies. Why should you have a range? Well, you can see straight away that because some electrons are easier to get out than others, that's the easiest one, I'm going to call it electron A, when that comes out, any surplus energy will be in the form of kinetic and it'll have a lot. This one, because it's more deeply embedded, is more difficult to get to the escape position, or more difficult to get out of the surface, as it were. So when it comes out, it won't have as much kinetic energy left over for it, as it were. So this electron will come out with a slower speed. And of course, there are electrons with a whole range of positions within the metal. So we've got to talk something like that. So what I've said, some electrons are harder to eject than others, as some are more deeply embedded than others. These will come out with smaller kinetic energies than the ones nearer to the surface, and that would do. What I then did, I said, well, I'm going to try and illustrate this. I'm going to label electron A, and it will come out with a greater kinetic energy than electron B.